Hello everyone, thank you for attending the talk. I'm Slava. I'm security researcher at Checkpoint for the past 5 years, and reverse engineering and vulnerability research is my daily work. 2 years ago, I did a research on Qualcomm DSP processors, and I have discovered several interesting security issues. And in those days, Qualcomm was a leading chip manufacturer of mobile devices, but the world is changing very quickly, and now it's time to switch to the new leader. It's MediaTek. So it was interesting for me to understand what MediaTek proprietary software is and how system-on-chip components interact with each other. In this study, I will introduce the MediaTek audio DSP for the first time as a target for security research, and I will show you a few zero-day vulnerabilities that could be used to attack audio DSP from application processor running Android and Linux kernel. Taiwan's MediaTek has been the global chip manufacturer starting from the third quarter of 2020. And as you can see on this slide, MediaTek SOCs are embedded in approximately 37% of all smartphone and IoT devices in the world, including high-end phones from Xiaomi, Realme, Vivo, Oppo that are highly popular in Asia. And moreover, according to the latest statistics, 43% of all smartphones sold in the second quarter of 2021 based on MediaTek SOC. So if you want to target Asian users, pay attention to the MediaTek software. I like this question, and I will ask it again. Do you know how many processors are on your mobile phone? You might be surprised. For example, the MediaTek Dimensity 1000 SoC, which is a high-end but not the latest SoC, contains 8 CPU cores, 9 GPU cores, 5 cores image signal processor, and a built-in 5G modem processor, and has several digital signal processors. Namely, this is a special artificial intelligence processing unit, APU, and the audio DSP that I used to improve media performance and reduce CPU usage. As you can see, the SoC is a complex thing, right? And most of the processors are managed by their own operating system, and this is not Android, as many people think. And today, we're going to talk about MediaTek proprietary audio DSP and its operating system, actually. The major goal of the research was to find a way to attack audio DSP from Android. And it would be right to start such investigation by understanding how Android communicates with the application processor. And obviously, there must be a Linux kernel driver, which waits for requests from the Android user space, and then using some kind of interprocessor communication forwards this request to the audio DSP side for processing. In this research, I used Xiaomi Redmi Note 9 5G smartphone based on MediaTek Dimensity 800 SoC. And as a test device, so there are only a few media-related drivers on my test device, and it was not really difficult to find the driver responsible for communication with the audio DSP. Actually, it has a clear name, audio EP. And a simple search for the driver name in the vendor partition allowed me to find the MediaTek API library, audio point, primary point, MTSO. This library exports a singleton which could be used to send EP messages, inter-processor interrupt messages from Android to audio DSP. I use this library, MediaTek API library, to explore the flow between Android user space and audio DSP. Yeah. In my test POC code, I have dealt with the driver ioctls directly without additional wrapping. And on the slide, you can see the ioctls that are most interesting for this study. And for example, there are 3 different ioctls for sending EP messages to the audio DSP from Android. And the difference lies in the way the message payload is transmitted. The possible options are to transmit payload as part of the message, or to transmit a payload through a memory shared between CPU and audio DSP, or it's possible to not to transmit the payload at all. Yeah. The audio EP-RegDMA ioctl could be used to request the driver to allocate a region and a dedicated shared direct access memory intended for communication between CPU and the DSP. Actually, 2 regions allocated per request. One is for transmitting data from CPU to DSP, and the second in the opposite direction. And as I have mentioned, the driver uses this shared memory, shared region, to transmit the payload when calling audio EP send DRAM ioctl, and to get results back from the audio DSP. Yeah. Okay, the EP message, which we can to transmit, has the following structure. And as I will show later, on the DSP side, there are several independent EP message handlers, call it task scenes, and each task scene has its own unique area of responsibility. For example, a phone call task controls speech enhancement. So in the EP message, we have to indicate what the task scene is related for, and also the message ID, which identifies the action that we are asking to do. In addition, we can to provide the data, some data for processing, and for this field property, for this purpose, there are 3 fields: the param1 and param2 double worlds, and the payload array. The payload can be either a data blob associated with the message ID, or an object indicated to the shared data. Okay, several words about shared memory. Okay, the audio EP-RegDMA ioctl, responsible for locating shared memory, expects to receive an object of the following structure as argument. And here we can control the size of the allocated region through the A to D size and D to A size fields. For this study, it means that we can transmit the message payload as large as we want. Okay. On my Xiaomi device, the Android kernel log has kindly provided us with information about the global dedicated direct access memory intended for communication with the audio DSP, and we have the baseness. We know the base address and the size of this memory, and it's really strange to log such information, I think. And moreover, when we're allocating a shared region in this DMA, the offset of the new shared region in the DMA is also logged. And for example, in this log snippet, you can see that for the task scene 18, I've asked to allocate 20 kilobytes of memory for A to D buffer and 19 kilobytes for the D to A buffer, and offsets are also here. Yeah. Now I will say a difficult thing. The physical address of the shared region calculated as a base address of the DMA memory and plus offset of this shared region in the DMA is persistent on the device. It means that if we rebooting the mobile phone, if after rebooting the mobile phone, we ask to allocate the same shared region, we will get the same physical address. So it's very good, and I will use it in one of the vulnerabilities I will show. To clarify, let's take a look at the following code that I have used to send EP messages from Android to audio DSP. And this code, first, we allocate DMA rec object, fill in the fields indicating that we need 4 kilobytes of memory for message payload, and then we call audio EP rec DMA ioctl to create the shared region. Okay. Next, we create audio EP message and put in their place param1, param2, task scene, message ID, and the payload data received as arguments of this function. And finally, we call the audio EP send DRAM ioctl to send the message and to transmit the payload through the shared region. Yeah. Great. So now we know how to send an EP message from Android user space to the audio DSP. The next step of the research is to research what is actually task scene and EP message handlers in the audio DSP firmware. And audio DSP is presented in the Xiaomi factory update by a separate audio DSP image file. Another way to get this image is to dump the audio DSP partition from a rooted device. And this image file has a proprietary structure, but it could be easily reconstructed. And on my test device, this image contains 9 partitions. The third one and third 2 partitions are certificates in DIR format that are used to verify integrity of the Hi-Fi 3 partitions. And each partition has a header that stores size and name of the partition, and header starts with a magic, which could be used to quickly locate a partition in the image. And for example, on the slide, you can see that the header and the data size of the Hi-Fi 3 ADRAM partition are 200 and 8,000 bytes respectively. And so I just want to say that we have all the information that we need to cut audio DSP content from the image. Yeah. Okay. The IRAM and SRAM partitions are code and data of the customized FreeRTOS, free real-time operating system. And DRAM is a dynamic memory, and in the initial state, it's almost empty. Let's take a closer look at the SRAM partition. The partition starts with 400 bytes. It means that there is no file format here, and we are dealing with the raw data. And next, about 4 kilobytes appear to be pointers to the memory, mostly located after 560000 address. And next, starting from the 3BF8 address in the Tensilica extensor bytecode. Yeah. Now let's talk about Tensilica extensor. Imagine you want to create your own highly specialized processor. How to make it super ultra fast? Okay. The general approach is to improve performance through the high clock rate. But there is another way is to adopt hardware for the algorithms running on it. And the MediaTek has chosen this second way. The Tensilica extensor platform allows a chip manufacturer to extend base extensor extraction set with custom instructions to optimize particular algorithms, and a researcher and the MediaTek developer can add their comments to perform operation on multiple data, or to encode several operations into one long opcode, or to combine several operations in another operation, etc. In short, MediaTek has been using the standard standard audio DSP template prepared by Tensilica for audio DSP processors, and that's it actually. Yeah. So we need to find a way to disassemble extensor code, and first I try to write a script that would try to find beginning of the functions and in the extensor code and try to disassemble. Theoretically, it's possible because most of the functions in the extensor begins with entry opcode that allocates the stack. And but this solution doesn't work because there are too many custom instructions that IDA is not aware of, and IDA just got stuck on unknown opcodes, and all that I have got are snippets like the following. Yeah. Eventually, I find a good solution is to use the extensor SDK to help IDA, and High5 DSP software development toolchain could be freely downloaded from the Tensilica Tools website, and the XT Dev Tools is a part of the installation packet. I use the XT object dump tool to dump High5 3 partitions of the audio DSP, and on the slide you can see the way I have dumped the SRAM partition. And the object dump contains disassembled extensor code, and the tool knows instructions where IDA got stuck. Yeah. Okay. Okay. But the object dump contains many errors actually, and cannot be used as a main resource for the research. But again, it can help either to parse, disassemble the High5 partitions much better. And the simplest solution is to use object dump to add disassembled code as a comment for all unrecognized instructions. Yeah. So on this slide you can see what the disassembled code and the IDA navigation bar looks like after applying the dump. And so almost called chunks were recognized. Yeah. Also, it should be noted that the firmware functions contains code to dump logging, to log debugging information, and the log message contains, among other things, the name of the current function, and means that MediaTek has gave us self-described function names and the ability to search for function name in the extensor firmware. Yeah. So, okay. For now, we know how to send messages from Android Audio DSP, and we know we have a way to research the Audio DSP firmware. So now let's take a look at the content of the firmware. Actually, MediaTek Audio DSP operating system is an adopted version of the FreeRTOS. MediaTek has used a third-party kernel and implemented messaging and audio media logic on top of it here. So, DSP operating system creates a number of audio tasks at startup and associates them with the SEN IDs. And the create all audio task function is a factory where we can find all the task scenes and task scene IDs and also. And on this slide, I've listed the audio tasks running on the test Xiaomi device, and I've highlighted the tasks that I have found vulnerable. Okay. The Audio EP driver, Linux driver, does not communicate with the Audio DSP processor directly. Instead, it forwards Audio EP messages from the Android user space to the system control processor, adding these messages to the SCPU, system control processor queue. And Audio DSP operating system registers SCP message dispatcher to get these messages. And each audio task is presented in the audio DSP operating system by a task object. And this object, amongst other things, contains a pointer to the receive message function, and the SCP message dispatcher calls these functions when a new EP message arrives. And actually, the receive message functions, that's what we are looking for. Because this is where audio tasks begin to handle audio EP messages, and the EP message is passed as a second argument to the receive message function. Yeah. So after a quick look at the extensor code and the audio DSP firmware, I see that most of the audio tasks, except phone call, upload, controller, and daemon audio tasks, use the same task common receive function, and there are only 5 listed on the slide functions that parse audio EP message, and this is where I looked for the vulnerabilities. I reviewed manually these 5 functions, and I discovered a few vulnerabilities that could be exploited to attack from Android the audio DSP processor. I will show you some details about vulnerabilities. For example, this vulnerability, is related to all common tasks, and when handling a message with ID6, task common task loop function copies the message payload to A2G share field of a task common object, and the param1 that we control is used as a number of bytes to copy. The check that the param1 is not greater than the size of the A2G share field is omitted, and hence the message payload overflows the heap after the A2G share field when the size of the payload is greater than 20 bytes. Yeah. On the slide also you can see the vulnerable code from the audio DSP firmware, and this call of the send EPDMA function that I have showed before, from Android, overflows the audio DSP memory and causes a crash. And here I asked to copy 600 bytes. And we don't have a crash dump, but Android kernel log contains the crash address actually. Yeah, it's not. This is the second write vulnerability, and so the task audio daemon task loop function upon receive of the message with ID 7 calls the initial core functions, which again copies the message payload to a heap allocated message buffer, and using the param1 as the number of bytes to copy. And this function contains the check that the param1 is less than E0. But the size of the destination buffer is 20 bytes, and this means that we can freely overflow C0 bytes in the heap, and to patch the audio DSP heap memory, it's enough to send the relevant EP message to the daemon audio tasks and transmit the message payload as a part of the message. That's all. Okay. This is the third write vulnerability. Okay, and when processing a message ID with 203, and the task common task loop functions, calls the get audio buffer from message function to extract an audio buffer from a physical memory addressed by the param2. And then this buffer is passed as argument to audio DSP hardware open op function, and this function copies this audio buffer to a static array. And the field in the offset 54 is used in the array, in the index of the array, and the check. There is no check for the index overflow. This means that if we can control audio buffer in the physical memory, we can provide arbitrary index and overwrite the memory in the data segment and with controlled values. Yeah. And to open this audio buffer, actually, it's enough to send an EP message and transmit a message payload through the shared memory, and indicate the param and point the param1 to the physical address of the shared memory. And yes, we know this physical address, and as I have mentioned, this physical address is permanent on device, and we know this address from the kernel log. Great. So we control the buffer, and the code represented on this slide just crashes my mobile test device here. Okay. What we have, we compromised audio DSP firmware, so we know how to send an EP message from Android from Android and overflow memory in the audio DSP. But to finish the flow, to this end-to-end flow, we need to find a way to attack Android HAL, Android hardware abstraction level from an unprivileged application. And we know how to trigger vulnerabilities in audio DSP using the audio EP driver iOctal, but unfortunately, Android application, unprivileged Android application, has no permission to communicate with this driver, because SELinux allows access to the audio EP device object only from factory, metatest, and MTK HAL audio contexts only. And so we need to find a way to exploit Android HAL to be able to send to call audio EP driver. Yeah. And while looking for a way to attack MediaTek HAL, I have found several dangerous audio settings implemented by MediaTek for debugging purposes. And an unprivileged Android application can abuse these settings to attack Android HAL. And Android documentation states that the audio manager provides access to volume and ringer mode control, and an application can bind the audio service and then call set parameter method of the audio manager to configure the hardware. Yeah. And a chip manufacturer can add its own audio settings parameters and keep track of their changes. As MediaTek has added the proprietary parameters to configure HAL Orisys libraries, and the MediaTek API library, audio point, primary point in TSO, parses these audio parameters and do the action actually. Yeah. So, for example, an unprivileged Android application can switch on, enable the logging of speech processing information just by sending this present on the slide parameter. The parameter string contains information about target subsystem. It can be ADSP or HAL. Also it contains Orisys scenario and command keys that identify the affected library and command name and its argument. Actually, all Orisys scenario and command keys we can find in the Orisys config XML file located on the device. And on this slice, I've combined all the accepted parameters. And the most interesting part is the command name, and on my test run device I found 9 possible comments, and all these comments are interesting for us in terms of information leak, but I want to pay attention only on one parameter, the param file comment. Okay, the param file comment allows an unprivileged Android application to indicate where is located configuration file for a particular Orisys library. Yeah. And actually, it should be noted that Android vendors and chip manufacturers don't care about check properly the configuration files, because them are not available for unprivileged users. But in our case, we control configuration files, and MediaTek HAL configuration becomes an attack vector, and an attacker can provide a malformed configuration file to crash a particular Orisys libraries, which could lead to local privilege escalation. Actually, this is all that I have the right to share with you about this vulnerability. I prepared it a simple example of abusing the API to attack one of the Orisys libraries, but I can share today for ethical reasons. So, what do we have? Okay. To summarize, we have looked at the MediaTek audio DSP as an attack target, and we show that an unprivileged Android application can attack the MediaTek HAL, and thus been able to send messages to the audio DSP, and a crafted audio DSP message could be used to execute and hide malicious code in the audio DSP firmware. And since the audio DSP has access to the audio flow, an attack on the audio DSP processor could be used to eavesdrop on the user. And since that DSP operating system works directly with the physical memory, it will be fine to continue this research and try to search a way to attack Android kernel from under the audio DSP. Yes. So MediaTek has decided to remove the ability to use the param file configuration through the audio manager in the release build of the Android. This vulnerability was fixed and will be published in the MediaTek Security Bulletin next month. And all the presented audio DSP firmware vulnerability also were fixed a month ago. Yeah. Actually, that's it. Thank you for your attention, and you can find many hardware-related security researchers on our Checkpoint research blog. Yeah, thank you. If you have any questions.
Thank you very much. This concludes the talk for today. The CTF prize announcers are in half an hour. If anybody has any questions, now is the time.
No, sorry.
No more.
Are you able to hear me?
Yeah.
Okay, so you said that you are able to compromise the DSP firmware. Was you able to bypass the integrity checks in the DSP firmware?
No, I don't know. Integrity checks, yes, you're right. I mentioned in the talk that there are certificates in the image of audio DSP, but this this integrity checks means that I can't, and nobody can, to change the Hi-Fi partitions to break the bootloading change process, but it doesn't mean that somebody from Android applications can send a message. Yeah, so we are not fixing the firmware itself. We just try to patch using this vulnerability the heap memory that is dynamic memory actually, and through this gain a local privileges. Actually, so it's certificates. It's not really related for this.
Okay. Thank you very much for the wonderful talk.
Thank you for the question.
Are there any further questions in the audience? No further questions.
So thank you.
Thank you all very much, and thank you very much to our speaker.